Hello, this is Shiyan from racetracksetup.com bringing you some nerdiness on a Friday night. So, Friday practice at the Istanbul track is over, and all the drivers are complaining of lack of grip from the new surface. Thought it would be interesting to revisit the topic of tires again. So after the it's a big topic this year. I was expecting it to be a big issue at Nürburgring due to the predicted cold weather and rain, but that didn't happen. So time to revisit the topic. So as explained in that video, the way grip is generated is coming from adhesion forces. So it's like molecular forces between the rubber and the road. I believe van der Waals forces. So that's one big part, but then the other part is the hysteresis grip. So basically coming from the interlocking between the tire rubber and the road. So as explained previously as well, the rubber is a viscoelastic element. So give it enough time, and it will kind of adapt its shape to the road. But of course, if the tire is too cold or you go for a compound which is really hard, then you can imagine then you just draw a straight line across the top of the stones rather than having the rubber fill in the gaps. And this is in fact also why when speeds increase, the grip from the rubber from tires decrease as well, because assuming there's no lift or downforce, then the rubber has less time to adapt its shape to the shape of the road. So when we think about a new track surface which has just been laid, then both the adhesion and hysteresis grip are likely to be lower. So the adhesion part is likely lower because of the oils that come out of the surface, but I suspect it's mainly the hysteresis grip, which is also a lot lower. And so looking at this very useful paper on ResearchGate, tires, so road have what is called the microstructure and macrostructure. So microstructure is like on these little stones, and probably even smaller stones, grains of sand. You could even think of it like that. There is like the size of the little bits, but then also each grain of sand might be different roughness. So that's the microstructure and the macrostructure. And the thing with new roads or newly laid asphalt is that everything will be nice and smooth, whereas with an older surface, it's all quite worn, and there are things for the tire to bite into, as shown previously on this page. So if you imagine in a very old track surface, there will be all kinds of these little elements sticking out, whereas on a very old surface, that's not. On a very new surface, it's all nice and smooth, so you don't get that benefit from what's called the hysteresis. But it's basically interlocking between the rubber and the road surface. So in this very useful paper, they also categorize, show how the categorization is there between microstructure, macrostructure, maga texture, and roughness. So if we then think about so what can the teams do about it? That's an interesting question. So the tires for this race were already chosen long before Pirelli was aware of the repaving of the track, which resulted in Pirelli bringing very very hard tires to this race. So that combined with the newly laid surface is causing the teams a lot of trouble. And the tire temperatures are very much on the low end. The teams have issues bringing the tires up to temperature. So if we now think about what the teams might try to do to get the tire up to temperature, because there's not that much you can do with the surface within one day. So there's, I've seen some funny stories where either the circuit operators or the teams are driving rental cars around the track to try and improve the track surface, but I think there's only limited amount that you can do with such measures. I think much more effective would have been a bunch of support races, but as they don't have that, that's not going to happen. So if you cannot do that much about the surface, then as the team, as a racing team, what can you do? So basically you have to think of ways to bring up the tire temperature. So then an obvious way is to try and get more of the heat from the brakes into the tire rim and then into the tire. So that's one. Some other possibilities would be to, say, increase the downforce level by increasing the downforce level. There is more. So if we go back a step, the teams obviously would have made some simulations to optimize their downforce level, considering the length of straights and the amount of corners and so on. And so they bring what they think is the optimal level of downforce in terms of the parts that they bring. But then, if the grip of the track is a lot lower than what they simulated, then obviously the downforce level that they had previously simulated as being ideal might not be ideal anymore. So that means if you increase the downforce level, so of course with a bit more downforce you go through the corners a bit faster, even if you have the same tire temperature, and you probably lose time on the straights. So assuming the same tire temperature, then simply increasing the wing level from what they simulated probably would end up with the worst result. But the issue is because the tires are so dominant, and if they can bring more tire temperature by increasing the downforce level, then it's probably worth doing. So then the gain that they get from the downforce, increasing downforce, is probably a lot higher than in a normal case. So we just said, okay, the first possibility is to try and get more heat from the brakes into the rim. The second is increase the downforce, and a third possibility that you normally wouldn't do is maybe run more toe in or toe out than you normally would. So if the tires are scrubbing along the track, normally you don't want too much scrub, of course, because that means more increased tire wear and increased drag from the tires. But if the tires are so cold that you cannot generate any grip, then you might turn to more desperate measures to get the tire temperature up. So maybe the teams might run more toe in or toe out. Which brings us to an interesting point in that Mercedes is running this. Mercedes F1 team is running this dual axis steering system, which is meant to not cause any tire scrub along the straights, but then have the toe out for the corners, for the corner turn in. But if you think about it, that is actually in this case counterproductive in generating tire temperature. So it could be that could be a reason why they are actually struggling a bit more compared to the other teams who don't run dual axis steering. So yeah, maybe they disable the system tomorrow. Who knows? Okay, so with that over, another interesting item which was in the news recently is this Tuatara record run, in brackets, where 331 mile per hour was claimed, but many famous YouTubers discuss how it might not have been possible, and that maybe only 240 mile per hour was actually reached. I've watched some of the videos. They're all quite interesting, and I would say the most theoretical one I've seen so far is quite a good video from Engineering Explained. In general, I quite like Engineering Explained. He brings out many formula which as an engineer it's quite nice to see. But I did notice a small mistake in his video. So if we look at what is maybe maximize the screen. So if we look at the
car, so we need a
if we look at the formula that is on the screen, it is most of it is correct. So power equals force times velocity, that's definitely correct. However, what he put as the force, so here he put power equals, so in brackets, an expression for force multiplied by v, the velocity. Okay, so the mistake is here. So force equals F arrow plus F roll. RR is rolling resistance, I assume. So there's nothing wrong with the formulas in here. It's simply that I believe he missed an important element. So if I bring up if we look at the Tuatara run, and it is something quite obvious when you look at the wait, that's not where what is it? Tuatara, a record run road. I'm trying to find a picture of that road. Yes, this one. And so if you look at that, what immediately jumps out at me is that it's not perfectly flat. There is a certain slope to it. So that means if you do a small free body diagram of the vehicle, here's the vehicle. Oh my, anyway. It's more banana, but you get the point, right? So, oh shit. Okay, sorry. So that's the road. You have some gravity. You have some rolled resistance. You have some rolling resistance. But the thing is, because there's a slight angle, there's as you run up it, there is also a certain element of gravity which is working against the vehicle going uphill as well. So, right, that out of the way. If we look at the formula in here, what is missing is the element that is the force which is caused by gravity. So anyway, to redo the calculation, so in fact the calculation for the Tuatara is, it doesn't actually take that long. We can so if we, and they're all things which everyone can just quickly Google for themselves. So for example, air resistance formula, FD equals half times rho V squared CD times A. So it means, so let's, okay, it's rho, but I'll just put P. That's the density of air. So let's just Google that. I know it, but just to show that it's quite easy to find density of air. Density of air. Try air. Density of air. So we can see it's about 1.2. Okay, sorry. So yeah, depending on the temperature, and so yeah, let's see, maybe it was 15 degrees, 1.225. Yeah, it varies, but okay, let's just take 1.225. That's kilograms per cubic meter. And then velocity, so let's see, that has to be in meters per second. So as SSC claimed 331, so times 1.609 to go to kilometers per hour, divide by 3.6 to get to meters per second. So yeah, 147 meters per second. And then CD. So the coefficient of drag, yeah, let's assume 0.3, which is, you know, ballpark number, and air cross-sectional area, 1.7 meters square meters is a ballpark number. And then for the rolling resistance, so I'm assuming no downforce, of course, but let's see, coefficient of rolling friction, tire, between tire and road, yep, 0 point, what? It's rather high. Coefficient of friction, that's not what I want. It's coefficient of rolling friction, rolling resistance. I want some values. Production bicycle tires, car tire measurements. Ordinary car tire on concrete, 0.01. Okay, so let's use 0.01. Whoops, that's the wrong one. Let's go back here. So, rolling resistance. CR 0.01. Okay, so let's work out the force. F drag is half, so 0.5, which is half, times rho times V squared. So let's just multiply twice. Multiplied by CD, multiplied by cross-section area. So that's the drag force, and then let's assume F rolling resistance is that times gravity. So G 9.81 times, let's assume that the Tuatara was maybe 1,500 kilos. So you can see, yeah, the rolling resistance is peanuts compared to the drag. All right, and then so the important thing is F slope. So that is the big unknown, because we don't know what, well, I guess we could try and find the slope of that road. And it will depend. Okay, so let's try. So let's try some numbers. Wait, no. First of all, so power. Let's try so total force is then sum of three forces. So for the moment the slope force is 0. Power is force times the velocity. That is in watts. We need to get that in horsepower. So that's watts, and then let's just Google horsepower. From what I remember is like 750-ish. Horsepower in watts. Oh, in kilowatt. Okay. 1 watt. I need the opposite. Okay, 1 horsepower equal to 746. All right, so equals that divided by 746. So it's saying the power needed is about 1,377 horsepower, but that's at the wheels. So then at the crank, let's see, typical drivetrain loss around 15.9%. Okay, so then equals that divided by 0.8441 to be precise. So it's saying you need about 1,600 horsepower at the crank. And what does the Tuatara have? Horsepower. Yeah, 1,750. So not that far off. Horsepower at the crank. At the wheel. So you need about 1,600 horsepower at the crank to go 331 mile per hour, assuming it's perfectly flat. So let's start trying angle. Let's say it's 1 degree. So if it's 1 degree, then the force becomes, let me think, is it the tangent or the sine? Well, in fact, for small angles, there's not much of a difference between tan and sine. So once again, let's assume 1,500 kilos multiplied by 9.81 multiplied by the sine of 1 degree. That actually becomes quite a significant force. But I have the impression I did something wrong. It's probably not the sine. What do you think about that? Is it a cosine? Anyway, let me try that. Cosine. I'm expecting a very small number. Okay. Is it in radians or something? That's funny. Am I going crazy? Sine just try that. Trigonometry. No, not sine of 0, sine of 1. Yeah, that's what I was expecting. So why is Excel giving me a hard time? Interesting. Returns the sine of an angle. Okay. Just to test out the theory that it's in radians, radian to, so if from degree to radians, I need to multiply by pi and divide by 180. Multiply by pi. 1, so it's pi by 180. Is that right? Yes. Ah, yes. That's why. Oh man. Okay. Okay. Excel's being rather tricky with me today. Okay. Okay, so it's not as significant as I thought. So if let's say if the slope is just 1, but it has resulted in a 50 horsepower difference, I believe. Wait a minute. Okay. Yeah, that's why. Forgot. Yeah. Okay. So, yeah. So now if we play with this, 1 degree adds about 60 horsepower. If it was 2 degrees, you get to 1,760. So these are all, but so it is saying, for per degree of road slope, roughly, you need another 60 horsepower at the speed that they were claiming. So the numbers say, despite the mistake in engineering explains calculations, if you have with about 1,500 horsepower and with some assumed figures of cross-sectional area and coefficient of drag, we come out to it being realistic. So of course, whether they really did it within the distance that they had to accelerate the vehicle and so on, we don't know. But it does seem feasible. So even if there was a 2-degree slope in the road, it is feasible if you have 1,750 horsepower at the crank. So hope it was interesting. Until next time.